Hello, let's talk about latent heat. So, we've already discovered that heat is, of course, the transfer of thermal energy that can be found using Q equals mc delta T. Another thing that this tells us is that as we change temperature, the energy increases or decreases. However, if you look at the slideshow, you'll notice that adding energy sometimes won't increase the temperature, or it won't decrease the temperature if you take away energy. And these are at certain points that we call phase changes. I can't remember which slide it's on since I'm not looking at the latent heat slideshow right now, but on one of the slides you'll see that as energy increases, temperature increases. But there are some points where you can keep putting energy into it, but for some reason the temperature doesn't the temperature doesn't increase, even though the energy is increasing. And these are at places that we call phase changes. We all know the three usual phases of matter that we talk about here on Earth. We talk about solid, liquid, and the gas phase. Excuse me. Of course, there are at least one more phase of matter, plasma, but we're not going to worry about that since that's not something that occurs naturally on Earth. So, if we're looking at these phase changes, these points where no more, the temperature won't change unless the phase changes. For instance, let's just say we have a solid object and you keep adding energy to it. Of course, it keeps heating up, but at some point, adding that energy won't cause the temperature to increase. Instead, it will change phase, going from solid to a liquid. Now, what we find is that it takes a certain amount of energy to change phases based on what the object is. And we call the amount of energy that an object must gain in order to change phase the latent heat. And if we're talking about going from solid to liquid, then we call it the latent heat of fusion. And if we're talking about going from liquid to gas, then we call it the latent heat of vaporization. Now, each material is going to have a latent heat of fusion, which is represented by capital L lowercase f, so L sub f, and each material will have a different latent heat of vaporization, which is capital L sub v. And one of the slides has a list of the latent heats of fusion and vaporization for some common objects. What you'll notice, especially for water, is that it takes quite a bit of energy to change phases. The latent heat of fusion of water is, and I'm going off of memory here, 3.3 times 10 to the 5th joules per kilogram of material, I believe. Make sure and check that chart, make sure I'm not giving you the wrong number. But what this means is that for each kilogram of water, or I guess in this case it would be ice, for each kilogram of this material, it takes that many joules, 3.33 times 10 to the 5th, in order to change phase. But what's important to start thinking about when we're looking at phase changes is that while the phases are changing, the temperature cannot change. So, for instance, let's just say we have an ice cube that is warming up from -5 degrees to 0 degrees. Okay, well, Q equals mc delta T. So we've got the mass, however much ice it is, maybe 2 kilograms of ice, times the specific heat of ice, which I can't remember off the top of my head. I want to say is 1900 joules per kilogram degree Celsius. He's around 2000 joules per kilogram degree Celsius. And then, of course, we've got the change in temperature. And the temperature is increasing from -5 degrees Celsius to 0 degrees Celsius. So that's 5 degrees Celsius as our change in temperature. But my point is that you can find out how much energy it takes to heat up that ice by using mc delta T. Q equals mc delta T. No problem. We've done that before. However, what if that same block of ice is going from -5 degrees up to 1 degree? We're going to have to add some more to that process, because we can't just do QC or Q equals MC delta T. I'm sorry, I can't talk today. We can't just do Q equals MC delta T, because we know that that ice will change phase. So for a situation like this, when we know a phase change happens, it will be Q equals MC delta T, but in this case, the delta T is just going to be the change in temperature while it's still ice. So -5 to 0 degrees. And then we have to add another term plus ML. And that L is going to be the latent heat of fusion. I will be adding a notes to the lecture section that has how the equation looks. But right now it would be Q equals MC delta T plus ML. And that ML is what I call the phase change part, right? Because we're going to have to add that much more energy in order to get that ice cube to change phase. But even after it changes phases, the liquid water now is still at 0 degrees. So if we want to heat that ice cube all the way up from -5 degrees Celsius up to 1 degree Celsius, then we have to do Q equals MC delta T, the delta T here being -5 to 0 degrees, plus ML, that's the phase change, plus another MC delta T term, because now that the ice has melted, it has to warm up from 0 degrees to 1 degrees. And that next MC delta T, the second one, will be the same mass, but this time it will be the specific heat of liquid water since it's changed forms. And that delta T and the second delta T will be from 0 degrees up to 1 degrees. So the point of all that I just said is that if an object is just changing temperature, MC delta T. But every time it changes phases, we need that ML term. And if it increases or changes in temperature after it's changed phase, then we need another MC delta T term. And of course, I'll be working examples. I think there is maybe 2 problems on the homework that talks about that specifically. But it's just very important to remember that every time it changes phases, we need an ML term. And every time it changes temperature, we need an MC delta T term. Let's see, what else did I want to specifically put in this video? I think that's all I wanted to do for the introduction of it. I've got some examples that I definitely want to work, so look for the new note section that I'm going to be putting on Blackboard by Wednesday evening. I'm going to get started on it this afternoon and get it finished up Wednesday evening. So that will be more examples of phase changes, examples of how to work homework problems, because some of the homework problems seem like they're completely out of left field. They take a lot of practice to get properly. So I definitely want to explain those a little bit more. And I know I went kind of fast on this video, but listen to it a few times and try to follow along. Of course, check in with the book. Check in with the slideshow, which doesn't give as much information as I want it to. The important parts on there, just remembering that it takes energy to change phase, and while an object is changing phase, it can't change temperature. So just look at all that. Of course, we'll be getting more notes. You may have seen the announcement, well, hopefully you did, that I have moved the homework and the test to next Thursday. Since we're not doing the final this semester, I just moved test 4 to be due when the final would normally be due, and also the homework assignment due next Thursday as well. So we still have time to work on everything. Of course, email me with your questions. If you've sent me questions today, I haven't checked my email yet. I wanted to get this video out first. So I'll get this posted. I'll be checking emails and replying to everyone. Let me know if you have questions. Thank you all very much for holding on, and have a nice afternoon.